In 1999, theoretical physicist James Gates was doing what physicists do, following equations wherever they lead. What he found stopped him cold. Buried inside the mathematics that described the fundamental behavior of the universe, not as metaphor, not as approximation, but literally encoded into the equations of reality itself. He found something that had no business being there: error-correcting codes. The same codes used in web browsers, in data transmission, in every computer system designed to protect information from corruption. Gates looked at them for a long time. Then he said something physicists almost never say in public. This is not science fiction. This is not a thought experiment. This is a documentary about peer-reviewed, mathematically verifiable evidence that the reality you're experiencing right now may not be what it appears to be. We're going to walk through every piece of it: the experiments, the equations, the scientists who got too close to the answer, and what happened to their careers. Because once you see this, you cannot unsee it. Let's start with something most people have never actually sat with. You believe you are sitting on something solid right now. A chair, a couch, the floor. Whatever it is, it feels real. It has mass. It has texture. Your body rests on it because it is, by any reasonable definition, there. Here is what physics actually tells us about that surface. Matter is almost entirely empty space. The atoms that make up what you're sitting on are, at the subatomic level, approximately 99.9999999999996% vacuum. The electrons orbiting the nucleus of each atom are so small relative to the atom itself that if you scaled a single hydrogen atom to the size of a football stadium, the nucleus would be the size of a marble at the center, and the electron would be an invisible speck somewhere in the upper stands. There is almost nothing there. What you experience as solidity, the sensation of physical resistance, is not atoms touching. It is electromagnetic force. The electrons in the atoms of your body and the electrons in the atoms of the surface you sit on repel each other. You are not touching anything, ever. What you feel as touch is the force between charges that never actually make contact. This is settled, basic, introductory level physics. This is what they teach in first-year university courses around the world, and yet almost nobody has actually processed what it means. This is where we have to start, because the question of whether we live in a simulation is not a question that lives in science fiction. It lives in physics, in mathematics, and in the strange, deeply unsettling gap between what we experience and what the universe is actually made of. To understand that gap, we need to go back about a century, to the moment when physics stopped making common sense. In the early 1900s, something happened to science that the textbooks don't quite convey. It wasn't just a discovery. It was a rupture. The old model of the universe, a vast, mechanical, predictable machine, governed by forces that operated the same way at every scale, simply broke. What replaced it was quantum mechanics. And quantum mechanics is, by the admission of every physicist who has ever worked with it, deeply, fundamentally, offensively strange. Richard Feynman, one of the greatest physicists of the 20th century, a Nobel Prize winner, a man who spent his career inside these equations, said this about quantum mechanics. Not, nobody fully understands it. Not, there are some confusing parts. Nobody understands it. A man who used quantum mechanics to make accurate predictions to 11 decimal places of precision said that nobody understands what it actually means. That is the world we are entering. And it is in that world, the world of quantum mechanics, that the simulation hypothesis finds its most disturbing, most scientifically rigorous evidence. Let's start with the experiment that broke everything. The year is 1927. The location is a physics laboratory. The experiment is so simple, a child could understand the setup. The results are so strange that 100 years later, nobody has a satisfying explanation for them. Here is the experiment. You have a source that fires electrons, subatomic particles, at a barrier. The barrier has two parallel slits cut into it. Behind the barrier is a detector screen that records where the electrons land. If electrons behave like particles, like tiny bullets, the pattern on the detector screen should be straightforward. Most electrons would pass through one slit or the other, and you'd get two bands of impact on the screen behind, one for each slit. That is not what happens. When you fire electrons through both slits, you don't get two bands. You get an interference pattern, dozens of alternating light and dark bands spread across the entire detector screen. The kind of pattern you'd get if you were firing waves, not particles, like dropping two pebbles in a pond and watching the ripples interact. Fine. Electrons behave like waves. Strange, but physicists could work with that. Then someone asked the obvious question, what if we slow it down? What if we fire just one electron at a time? Surely a single electron has to go through one slit or the other. It can't interfere with itself. So they did it. They fired electrons one at a time, and they waited. And they watched each individual electron land on the detector screen, one at a time, over hours, over days. And when they stepped back and looked at the accumulated pattern of individual electron impacts, it was an interference pattern. A single electron, fired alone, with nothing else in the experiment, had somehow passed through both slits, simultaneously, interfered with itself, and landed in a position that only makes sense if it traveled as a wave through both openings at the same time. But that was not the strangest part. The strangest part came when someone decided to watch. Physicists placed a detector at the slits, a measuring device that would record which slit each electron actually passed through. Not interact with it, not stop it, just observe which path it took. The interference pattern disappeared the moment the experiment included a way to determine which path the electron took. The electron stopped behaving like a wave. It started behaving like a particle. It went through one slit or the other. The wave-like interference pattern vanished, replaced by exactly the two bands you'd expect from classical particles. Then they turned the detector off again. The interference pattern came back. On, off, on, off. Every single time, without exception. The act of observation, the presence of a measurement device, whether or not any human eye was actually watching, changed the behavior of the particle. Reality, at the fundamental level, behaved differently, depending on whether it was being measured. Physicist Niels Bohr, one of the founders of quantum mechanics, tried to explain this with what became known as the Copenhagen interpretation. His position was essentially, quantum systems exist in superposition, a kind of probabilistic blur of all possible states, until observed, at which point they collapse into a single, definite outcome. This means that prior to observation, the electron wasn't really anywhere in particular. It existed as a probability wave, a mathematical description of all the places it might be. The act of measurement didn't just reveal where the electron was. It determined where the electron was. That is not a metaphor. That is the literal mathematical formalism of quantum mechanics. The wave function collapses upon measurement, and this is where it connects directly, uncomfortably, to the simulation hypothesis. Think about how a video game renders a world. An open-world game, something like a massive role-playing environment, does not render the entire world at once. That would require impossible computing power. Instead, it renders only the portion of the world that the player is currently looking at. The moment you turn your character away from a mountain, the mountain stops being fully rendered. It is held in a compressed state until you look at it again. The universe behaves identically. Quantum systems don't resolve into definite states until observed. They exist in superposition, a compressed, unresolved state, until a measurement forces them to commit to a single outcome. The act of observation, of looking, triggers resolution. This is not a poetic analogy. The mathematical structure is the same. And the physicists who noticed it first were not conspiracy theorists. They were the most rigorous mathematical minds of the 20th century, and they spent decades arguing about what it meant because the implications were too large to accept comfortably. John Wheeler, one of the great physicists of the modern era, spent years developing what he called the participatory universe. The idea that observers are not passive witnesses to a pre-existing reality, but active participants in bringing reality into existence through the act of observation. He famously asked, "Is the universe a self-excited circuit, a system that brings itself into being through the act of being observed?" He did not have an answer. He wasn't sure anyone ever would. But the question, the serious, mathematical, peer-reviewed question of whether reality only fully exists when it is being computed, that question did not go away. It got louder. And in the early 2000s, a philosopher named Nick Bostrom gave it the most rigorous, formal treatment it had ever received. But before we get to Bostrom, we need to talk about something even more fundamental. Something that suggests the universe doesn't just behave like a simulation. It may have a frame rate. In 1899, a German physicist named Max Planck was working on the mathematics of thermal radiation. In the middle of his calculations, he noticed something peculiar. There appeared to be a natural minimum unit of length, a smallest possible distance, below which the concept of distance itself stopped making sense. He called it the Planck length. In physical terms, the Planck length is approximately 1.616 times 10 to the negative 35 meters. To put that in perspective, a hydrogen atom is already 10 to the negative 10 meters. The Planck length is 10 to the negative 35. It is 25 orders of magnitude smaller than an atom. It is inconceivably, incomprehensibly small. Planck didn't know what to make of it. He filed it as a mathematical curiosity, a limit that appeared in the equations, but might not have any physical significance. He moved on. He was wrong to move on. What the Planck length actually represents. And this is the part that does not get nearly enough attention, is the smallest possible length scale at which the current laws of physics continue to make sense. Below the Planck length, space and time, as we understand them, break down. The mathematics stops working. Not in a way that suggests we need better mathematics. In a way that suggests there may be nothing below this scale to describe. The universe appears to have a minimum pixel size. Every screen you have ever looked at has a resolution limit, a point at which you cannot zoom in any further because there is nothing smaller than a pixel. Below the pixel, there is nothing, or rather, there is only the computational substrate that generates the image. The Planck length is the pixel of reality. Now, this is where the conversation gets serious. In 2013, a team of physicists at the Fermi National Accelerator Laboratory, Fermilab, one of the most prestigious physics research institutions in the United States, ran an experiment called the Holometer. The purpose of the Holometer was to test a hypothesis called the holographic principle. The holographic principle, first proposed by theoretical physicist Gerard T. Hooft and later refined by Leonard Susskind, suggests something extraordinary, that all of the information that describes a three-dimensional region of space can be completely encoded on a two-dimensional surface surrounding that region. In other words, what appears to be a three-dimensional universe may be a projection, a holographic rendering of information encoded on a lower dimensional surface. Like a hologram, a two-dimensional film that projects a three-dimensional image. The holographic principle is not fringe science. It emerged from serious work in string theory and black hole thermodynamics. Stephen Hawking used it. Juan Maldacena built one of the most celebrated pieces of theoretical physics of the last 30 years on top of it, the ADS/CFT correspondence, which has been called the most important theoretical physics paper of the modern era. The Fermilab Holometer was designed to test whether the holographic principle has a physically detectable consequence, specifically whether there is a fundamental graininess to spacetime at the Planck scale that would show up as a kind of cosmic noise, a quantum jitter in the fabric of space itself. The experiment ran. It produced results, and those results were strange. The holometer detected correlated noise in the two independent interferometers, noise that was not explained by any known physical source. While the team was careful not to make claims beyond what the data strictly supported, the results were consistent with a previously proposed model by physicist Craig Hogan, who had calculated what holographic noise would look like if the universe were genuinely holographic. This does not mean Fermilab proved we live in a simulation. No serious scientist would say that. What it means is that the universe behaves as if it has a fundamental resolution limit, a pixelated structure at the smallest scales, and that this structure produces measurable physical effects. Then there is James Gates. We heard his name in the opening. Let's go back to him now, because his discovery deserves more than a quote. Dr. S. James Gates, Jr. is a theoretical physicist at Brown University. He spent his career studying supersymmetry, the mathematical framework that attempts to describe the fundamental symmetries of the universe. This work involves equations of extraordinary complexity, the kind that fill entire blackboards and take years to develop. While working on these equations, Gates found something embedded in the mathematics that describe how quarks, the fundamental building blocks of matter, interact and transform. He found a class of mathematical objects called doubly even self-dual linear binary error-correcting block codes. These are the same codes used in computer systems to detect and correct errors in data transmission. They are the same codes that protect your browser when you send an encrypted message. They are fundamentally the tools of computation. They had no business being in the equations of fundamental particle physics. There was no theoretical reason for them to appear. They were not put there deliberately. They emerged from the mathematics themselves. Gates published his findings. He spoke about them publicly. He did not sensationalize them. He simply described what he had found and said what it suggested to him. That reality, at its mathematical foundation, appears to have the structure of a computation. He was careful. He was rigorous. He did not use the word simulation. He simply said that what he found looked like codes, and that codes, in his experience, implied a coder. Then there is the work of physicist John Barrow, who pointed out something deeply unsettling. If our universe were a simulation, it would almost certainly contain errors, moments where the simulation ran out of processing power or where its constraints became visible. Barrow called these simulation glitches, and he suggested that the best place to look for them would be in the fundamental constants of physics, numbers like the speed of light or the charge of an electron, which, in a simulation, might occasionally shift slightly as the simulation adjusted its parameters. Here is the uncomfortable part. The fundamental constants of physics do appear to change over cosmic time. The variation is tiny, disputed, and not yet conclusively established. But multiple independent teams of astronomers studying ancient light from distant quasars have reported evidence that the fine structure constant, one of the most fundamental numbers in all of physics, may have been slightly different in the early universe than it is today. Not because of any known physical process, just different. We now need to step back from the physics for a moment and ask a different kind of question. Not what the universe is made of, but what the universe is for. And for that, we need the most important philosophical argument for the simulation hypothesis ever constructed. In 2003, a philosopher at the University of Oxford named Nick Bostrom published a paper. Its title was, "Are You Living in a Computer Simulation?" It appeared in the Philosophical Quarterly, one of the most respected academic philosophy journals in the world. The paper was not speculative. It was not a thought experiment in the loose, informal sense. It was a rigorous, logical argument with a mathematical structure. And its conclusion was not that we are living in a simulation. Its conclusion was something more unsettling, that at least one of three propositions must be true, and two of those three are deeply disturbing, while the third is the most disturbing of all. Bostrom called it the simulation trilemma. Here it is. Proposition 1. Almost all civilizations at our level of technological development go extinct before reaching the capability to run detailed simulations of their ancestors. Proposition 2. Almost all civilizations that do reach that technological capability choose not to run such simulations, whether for ethical reasons, lack of interest, or some other factor we cannot currently anticipate. Proposition 3. We are almost certainly living in a computer simulation right now. The logic works like this. Human civilization has existed for roughly 200,000 years. We have been capable of running simple computer simulations for less than 100 years. In that time, we have gone from rooms of vacuum tubes to devices that fit in your pocket and can model physical systems with extraordinary fidelity. Project Forward. If human technological development continues, if we do not destroy ourselves, what will our simulation capabilities look like in 1,000 years? In 10,000 years? In 1,000,000 years? At some point in that trajectory, if it continues, we will be capable of running simulations of ancestral civilizations. Not rough approximations, full, detailed, subjectively convincing simulations of human experience, complete with simulated minds that are indistinguishable from biological ones. Now ask, how many such simulations would we run? Given what we know about human behavior, our fascination with history, our interest in scientific experimentation, our love of games, the answer is almost certainly a very large number. Many simulations, perhaps millions, perhaps far more. If a single civilization reaches this capability and runs millions of simulations, then the number of simulated conscious minds vastly outnumbers the number of biological ones. In that scenario, for any given conscious mind, including yours, including mine, the overwhelming probability is that it is simulated rather than biological. The only way to avoid this conclusion is to argue that one of the first two propositions is true, that almost all civilizations either go extinct before reaching this capability or choose not to use it when they have it. And here is the devastating part of the argument. Even those escape routes have dark implications. If civilizations consistently go extinct before reaching simulation capability, that suggests something, some filter, some inevitable catastrophe that destroys civilizations at a predictable point in their development. Something that is waiting for us too. And if civilizations consistently choose not to run simulations despite having the capability, why? What do they know? What do they discover about the nature of simulation that makes them stop? There is no comfortable version of Bostrom's trilemma. Every exit leads to somewhere dark. Bostrom's paper was published in 2003. By 2016, it had been cited by leading cosmologists, physicists, and philosophers worldwide. Elon Musk stated publicly that he believes the probability of our reality being base reality, not a simulation, is 1 in billions. Astrophysicist Neil deGrasse Tyson gave the simulation hypothesis a 50-50 chance of being correct at a major scientific symposium. These are not fringe thinkers. These are the most prominent scientific communicators in the English-speaking world. So why isn't this the biggest news story in the history of human civilization? Why are we still arguing about traffic and interest rates, while one of the most rigorous arguments ever constructed suggests there is a non-trivial probability that none of it is real? Part of the answer is psychological. Human beings are extraordinarily good at ignoring information that threatens the foundation of their daily reality. This has been studied extensively. It is called normalcy bias, the tendency to assume that the world will continue to function as it always has, even in the face of evidence that it might not. But part of the answer may be something more deliberate. And this is where the story gets complicated. In 2017, theoretical physicist Sabine Hossenfelder published a paper arguing that the simulation hypothesis, while philosophically interesting, was fundamentally untestable, and therefore not science in the strict sense. This was a widely circulated argument, and it was used by many mainstream commentators to dismiss the hypothesis entirely. The problem with that argument is that it proves too much. For most of its history, the theory of the atom was untestable in the strict experimental sense. The multiverse, currently the dominant theoretical framework in cosmology, is, strictly speaking, untestable. String theory, which has absorbed the careers of thousands of the world's best physicists for 50 years, has produced no testable predictions. By the standard applied to the simulation hypothesis, none of these are science either. The real question is not whether the simulation hypothesis is testable in principle. The real question is whether anyone is seriously trying to test it, and what happens when they do. The Fermilab Holometer was the most serious attempt. When its results were published in 2015, they received brief media attention, were characterized as finding no evidence of holographic noise, and were largely dropped from public discourse. The characterization was not entirely accurate. The holometer found no evidence of holographic noise in the specific frequency band and specific model it was designed to test. But the existence of holographic structure at other scales or describable by different models was not ruled out. Craig Hogan, who designed the theoretical framework for the experiment, continued arguing that the results were not conclusive, and continued his work. This distinction between failing to find evidence for one specific model and disproving the broad concept is significant. It received almost no coverage. Then there is the story of Thomas Campbell. Campbell is a physicist, formally trained, with a career background in missile defense research for NASA. In the 1970s, he began a decades-long investigation into the nature of consciousness and its relationship to physical reality, eventually producing a unified theory he calls My Big Toe, a theory of everything, which frames the physical universe as an information system generated by a form of consciousness. Campbell's work draws directly on quantum mechanics, on the observer problem, on wave function collapse, on the measurement dependence of reality. His framework is mathematical, coherent, and internally consistent. It makes specific, testable predictions about quantum mechanical experiments that differ from the predictions of standard quantum interpretations. In 2017, Campbell partnered with physicists at universities including the University of California and others to design a set of double-slit experiments specifically intended to test his framework's predictions. The experiments were proposed, designed, and began seeking funding. They had extraordinary difficulty getting institutional support. This is not evidence of a cover-up in the dramatic sense. Funding for physics research is genuinely limited, and unconventional theories face real barriers to institutional support, barriers that exist for legitimate reasons, since resources are finite and most unconventional theories are wrong. But it is worth noting which ideas struggle for institutional support and which ones sail through. The simulation hypothesis, despite having been endorsed or taken seriously by some of the most credentialed scientists and philosophers alive, consistently struggles to attract the kind of serious, well-funded research attention that would be needed to decisively test it. There is a reason for this that goes beyond funding scarcity. If the simulation hypothesis is true, if there is any serious probability that it is true, the implications for every institution on the planet are catastrophic. Religion, government, law, economics, social structure, all of these assume a baseline reality that is given, fixed, and shared by all participants. The simulation hypothesis does not merely question whether God exists. It questions whether the substrate on which God, government, law, and society would operate is itself real. An institution that takes the simulation hypothesis seriously and allows that seriousness to propagate into public consciousness, is an institution that is potentially sawing off the branch it sits on. That is not a conspiracy. It is an incentive structure. And incentive structures, over time, produce the same outcomes as conspiracies, without requiring anyone to meet in a dark room. So let us sit with the question seriously for a moment. What does it actually mean if this is true? If the simulation hypothesis is correct? If the physical universe is an information system generated by some form of computational substrate? Then a number of things follow that are deeply strange, but not necessarily terrible. First, consciousness may be more fundamental than matter, not less. The standard model of physics treats consciousness as an emergent property, something that arises from sufficiently complex arrangements of matter. But in a simulation, consciousness is not emergent. It is the point. The simulation exists to generate experiences for conscious observers. Matter is the rendering medium, not the thing being rendered. This is not a new idea. Variants of it appear in every major philosophical and religious tradition in human history. The Vedic concept of Maya, the world as appearance rather than ultimate reality. Plato's allegory of the cave, shadows on a wall mistaken for the real. The Christian concept of a created world that is less than God and points toward God. The Buddhist teaching that the self and its objects are empty of inherent existence. None of these traditions arrived at their conclusions through quantum mechanics. But all of them arrived at a conclusion that quantum mechanics also points toward the world we experience may not be the deepest level of what is real. Second, if the universe is a simulation, then the so-called laws of physics are not laws. They are rules, parameters, code. And rules, unlike laws of nature, can in principle be changed, can be overridden, can produce, under certain conditions, results that look miraculous from inside the simulation. This is why the simulation hypothesis has been called, by various thinkers, the first genuinely scientific framework for understanding phenomena that science has previously refused to engage with. If reality is computational, then what we call the impossible may simply be a region of the rule set we haven't mapped yet. Third, and this is perhaps the most important thing, if we are in a simulation, then the simulators existed before the simulation, which means the simulation is not all that exists. There is something outside. The universe having an outside is one of the most extraordinary propositions in the history of human thought. And yet every framework we have developed for understanding quantum mechanics, from Copenhagen to many worlds to pilot wave theory, points towards something that interacts with the physical universe from a position that is not fully inside it. The wave function is not inside spacetime in the way that tables and chairs are. The mathematical structure of quantum mechanics reaches outside the box. There is a final thing to say, and it is perhaps the strangest of all. If you are a conscious observer, if you are here experiencing this, processing these words, then in any computational framework, you are not merely an object inside the simulation. You are part of the system by which the simulation renders itself. The observer who collapses the wave function, the eye that makes the pixel. John Wheeler's question, is the universe a self-excited circuit, may have an answer, and the answer may be yes. And you may be one of the circuits. This is why it was buried. Not because it is dangerous in the political sense, not because anyone sat in a room and decided to suppress it, but because it is dangerous in a deeper way. It suggests that the most fundamental assumption of modern civilization, that we are material beings in a material world, navigating fixed physical laws toward comprehensible ends, may be wrong. Not metaphorically wrong, mathematically wrong, physically wrong, structurally wrong. And the institutions that rest on that assumption, which is all of them, have every structural reason to treat the simulation hypothesis as a curiosity rather than a crisis. Whether they are correct to do so is a question that physics has not yet answered. But it is also a question that physics has not yet been given the resources, the freedom, or the institutional urgency to seriously pursue. The experiment that would answer it may already be possible. It may simply not yet have been run. Here is what we know. We know that at the quantum scale, reality does not behave like a pre-existing fixed environment. It behaves like a system that resolves information on demand, only when observed, only when measured, only when a conscious agent requires a definite answer. We know that the universe appears to have a minimum length scale, a pixel, below which the concept of space ceases to make sense. We know that embedded in the equations describing the fundamental interactions of matter, a theoretical physicist found codes of the kind used in computational systems. Codes that had no reason to be there, and yet are there, mathematically, undeniably. We know that a rigorous logical argument suggests that if any civilization in the history of the cosmos has ever survived long enough to develop simulation technology and chosen to use it, then the overwhelming majority of conscious minds in existence are simulated rather than biological. We know that mainstream science has not seriously pursued the testable implications of these observations, and we have explored some of the reasons why. What we do not know is the answer. We do not know whether the universe is a simulation. We do not know who or what would be running it. We do not know what exists outside it. We do not know whether that question is even meaningful, or whether our concepts of inside and outside break down at that level, just as our concepts of space and time break down at the Planck scale. What we do know is this: the question is real. The evidence is real. The mathematics is real. And the scientific establishment's discomfort with following these threads to their conclusions is, itself, a data point worth noticing.